You're going to want to write this stuff out, believe me. Now, one of the reasons that I'm getting at this whole idea of what I'm kind of putting it as like this little how-to is, as you go through math, there are ways that we introduce topics to you guys, and then after we introduce topics, we start to go further into them and explain why they work and how these things are all interrelated. And one of the things that you guys first learned when we talked about what are called quadratics or called trinomials, things like that, you learned this. You first saw what was called a quadratic written like this. This idea of something called ax squared plus bx plus c, and that was equal to 0. That's called a trinomial. A trinomial means there are three terms separated by addition or subtraction, and usually what happens is they go from what we call a decreasing in degree. Degree is the exponent. What you guys basically worked with up till this point is what we call second degree polynomials. Second degree just means it's a squared term. Polynomial just means multiple term. When you guys go further on into math, like you'll have to with next year, we actually talk about what are called nth degree polynomials. What that means is that you're going to have, x to the fifth plus 4x cubed, and so on and so on and so on. And we will still be able to figure out and how to factor all that. Because the rules of factoring don't change whether or not it is a second degree term, an nth degree, or fifth degree, or whatever. All those rules still hold true. But when you first talked about this idea of what we call a quadratic, when we first learned about that, you guys started doing stuff with graphing. Remember you talked about what was called that axis of symmetry? How these guys all created some sort of what we call a parabola? One of the first lessons you guys go in once you're introduced to what we call a trinomial is that we start plotting points and learning about what it looks like visually. What these squared terms do is that they have a curve to them, and in between that curve, there's this imaginary line which we call the axis of symmetry. That imaginary line between the curves, each point on the curve is always the same distance to that axis. All right? Those points on the outer edges, those points we always call symmetric twins. This point here is 4 spots away, this point's 4 spots away. They're the same value horizontally. It's called a symmetric twin. As you went further with that then, you learned that if you graphed this curve could, in fact, cross the x-axis. Now, when something crosses the x-axis, that means that the value of y for its ordered pairs, remember, points are just ordered pairs, some x coordinate, some y coordinate. The y coordinate, every time you cross the x-axis, is 0. So what happens here is that this value of x, whatever this value is, if you substitute into here and here, it generates this value of y, which is 0. So when it crosses that x-axis like that, it's actually figuring out what's called the zeros. It creates what are called zeros. Now, when you did it this way, you had to do all this graphing, you had to do all this other stuff, and it was a big, giant pain in the butt to do because there's a lot of steps to it. just like other types of math, the more complicated things start out with, there's probably a shortcut somewhere along the line, somewhere along the way that you could allow you to do this. Okay? That's kind of where factoring comes into play. Now, if you take this a semester earlier than where we're at right now, this whole idea of this curves. Do you guys remember graphing lines? Remember when you graphed lines and you had to figure out where two lines intersected? Let's say y equals negative 2x plus 1. Let's say you had to figure out where two lines intersected. You guys would have plotted them, put them on a piece of graph paper, and hope to God that you got the right coordinates and you were able to find something that landed on an integer, a whole number, so that way you can figure out where these two intersected. But God forbid that it landed halfway in between something, you'd have to kind of guesstimate. Well, again, there was this complex way of doing this, of working through and walking with slopes and stuff and plotting values. Going the other way, put this one in blue. Oops. And you see how those two values intersected at an ordered pair. That ordered pair would be called then a solution set. It was a set of values where if you substitute in that x value for either equation, it'll generate the same y value for either equation. It meant that at 1, negative 1, negative 2 times 1 plus 1, well, that equals negative 1. 3 times 1 minus 4 is negative 1. That meant that long-form way of graphing, you were able to figure out an answer that meets the problem. After you did that for a day or two, you're kind of like, man, this sucks. It takes forever. That's when we introduced you guys to what we call systems of equations. So when you talk about that, systems of equations, hey, that means, look, I got two things that both equal y. When two things equal the same thing, what do we know about those? They equal each other. And we did that already this year. So same basic idea of this substitution step that you've done algebraically, saying that negative 2x plus 1 is 3x plus, 3x minus 4. I know that those two have to be equal because they both equal the same variable. And I know that I can move the negative 2x by adding. I can move the negative 4 by adding. And I get 5 is 5x. And look what happens to equal x. 1. And if I take 1 and I substitute back in here, look what I get. Negative 1. So you went from something that was complicated by, you hungry? You went by something that was complicated by graphing, where you can do so many stupid things wrong, to showing, hey, there's an easier way to do this. Let's use algebra to make our lives easier. That's why we did it like that. It's kind of the same idea here. You could graph these equations all day long, figure out where they cross the x-axis, but it's a pain in the butt. It really is not any fun to do at all. But if we understand the idea that, hey, I can take a trinomial and turn it into what are called terms, x, I don't know, there could be plus something, it could be a number in front, whatever. I can break it into smaller chunks to figure out what generates a value of 0. It becomes an easier process to work with than graphing. So you're taking these ideas of chunk times chunk equals chunk times chunk, or outside times the whole equaling outside times the whole. You're taking these ideas of, in a geometry setting, how do I make the algebra give me the answer, okay? So what I want to work with you guys today is I think I've got 3 or 4 examples of just pure factoring. Why does it work, and what is the best way to do it? And I'm going to fall back on the old-fashioned way of multiplying your tails to add to the middle, okay? So let me go show you that. Where is it? Sorry, I thought I had it open. Too many tabs. There we go. I'm going to start really, really, really easy. If I start with something like this. Excuse me. If I start with something like this, where I have x squared minus 3x minus 4 equals 0. That is my trinomial. That is my quadratic, if you will. It's the big one. It's the big picture. In order for me to be able to figure out what value of x, or what values of x make this equal to 0, I have to do some factoring. Oh, let me ask you this real quick. Have any of you guys ever heard of what's called the fundamental theorem of algebra? I'm sure you have. Okay. What's the degree of this problem? 2. When you have a degree of 2, that tells you that you can have at most 2 answers, 2 zeros. When you have a 3rd degree polynomial, that means you can have at most how many answers? 3. If you have a 5th degree, you can have at most how many? If you have a 1 degree, at most how many can you have? 1. The fundamental theorem of algebra, which we talk in length about in Algebra 2, basically tells you you could have as many zeros as the highest degree in the problem. Okay? That means that it could cross the x-axis twice. If it was a 3rd degree, it could cross it 3 times, 5 times, and so on and so on. Okay? There's a lot of little things that you'll learn with that. So here, I know I'm going to have 2 terms because it's squared. So what's the number in front of the x squared that you just don't see? It's a 1, okay? That's called a coefficient. We all know that, right? So if I just put that there for right now, what I mean by multiplying my tails, I'm going to take 1 times negative 4. What times what is negative 4 that adds to my middle term of negative 3? So basically what I wind up doing here is I'm going to list all of my possible factors of 4 and then mess around with my signs. Okay? So my possible factors of 4 are 1 times 4, 2 times 2. Yeah, it has to be 1 and 4. Now, this is where a couple other little bits of math comes back in to make sure that you remember. When you multiply 2 numbers together to be negative, that means 1 has to be negative. All right? If if the 2 numbers multiply to be negative and they add to be negative, that also means the bigger of the 2 numbers was negative. If they multiply to be negative and they add to be positive, bigger 2 would be positive. It's those little tricks that you probably don't think too much about that do come back into this. That helps you to maintain what your signs are, okay? Your SIGNs, the positives and negatives. So here, obviously, it's not going to be 2 and 2 because that gives me 0. So which of these 2 has to be which one of those 2 has to be negative, the 1 or the 4? The 4. Good. So whenever you have that first term that doesn't have a coefficient other than just 1, you can just go right to your terms. Terms are always the things that go in parentheses. Your terms of polynomials of any type always generate zeros. Terms create zeros, and zeros can help you determine terms, back and forth. Bless you. I know that x's have to go in both of them, and one of them is +1, and the other one is -4. Could I have written it as x minus 4 and then x plus 1? Yeah, it's okay. When you put them back in, it doesn't matter which spot they go in because you're going to be multiplying it all out anyway. You know, because basically what you're doing here is you're unfoiling something that's been foiled and simplified. Okay? So at this point, you now have two terms that are both equal to 0, which means that either one of them, since they're being multiplied together, could equal 0. So you need to figure out what value of x makes either term 0. That's why I say just do this and solve for x. If you set both of your terms equal to 0, that's the idea of the term generating the 0. How do I move the positive 1?
Subtract it.
Subtract it. How do you move a negative 4?
Add it.
That generates zeros of that function at negative 1 and 4. Which means graphically, if you had to do this like you did back last year, you would have done something like this, found your vertex and done all that and found your missing ordered pairs. Okay? You would have had to have done all of that work to get to it. But by factoring, it gets you there quicker. All right? It gets you there quicker.
Yep.
And it doesn't change as numbers get funkier or larger or anything. We still do the exact same scenario. Things don't get weird until we have to worry about really the first term. So if I have x squared, 19x, and an 88, where everything's positive, so it's x squared plus 19x plus 88. Since all three parts are positive, what do I know that about my two terms? What do they both have to be? What's that? Positive. They both have to be positive because I'm looking at what two numbers multiply to 88 positively that add to a positive 19. And yeah, again, it sounds weird, but if you go through some of your factors, more often than not, we're not talking about crazy large numbers that it's going to be awful to have to go through. Okay? Now, this one's pretty quick. It's 188, 244, 422. Oh, do you guys know the rule for threes? Well, what's the rule to tell whether or not something's divisible by 3? Do you remember that? Let me show you. What's 8 plus 8? Is 16 divisible by 3? No. So 88 is not divisible by 3. That's how you do it. If it was 188, you do 1 plus 8 plus 8. 17. Is 17 divisible by 3? No. If it was 288, 2 plus 8 plus 8 is 18. Is that divisible by 3? Yeah, so 288 is divisible by 3. That's how those tricks work. Okay. 4, it's not 4, I think it's 6. I think 6 works if 2 and 3 work, if I'm not mistaken. Because 2 times 3 is 6. Then this one goes to, I think it just goes to 8 and 11. Which one of those combinations, if you add them together, gets you 19? 11. So again, since this was a 1, I multiplied here to add to the middle. I can go right into my terms by writing out x plus 8, x plus 11. So now you have two terms. The two terms, therefore, generate your zeros. So if you do that, you're setting both of them equal to 0. What plus 8 is 0? Negative 8. And what plus 11 is 0? 11. And those would be the answers to this problem. Now, it's not, we haven't taken this back into a geometry setting yet where more often than not negatives didn't work for us, but algebraically, it is a true statement. So algebraically, that's why we have to set this up. You're using multiple parts of math that you've gone through in just a different setting. That's kind of why we use factoring. Factoring is something that doesn't go away. My honors algebra 2 class, they actually have to factor with trig functions. Okay? You guys probably won't do that in a regular algebra class. You'll probably do a little bit of, you might do like sine squared minus 1 and have a difference in squares or something like that, but the idea of the factoring doesn't go away really through anything. I know in pre-calc we did a lot of factoring as well. It's that circular thing of math that no matter what, when you've learned it once, it's presented once, 9 times out of 10, it's going to come back again. Okay? Really, the only topics that I can think of off the top of my head that you don't really see a lot of again, proofs. You do a little bit here and there, but they're not going to say, hey, write the show the proof of why this triangle does this. No. Okay. Yes, ma'am. Yeah. What changed now? It's not a 1 in front of the x squared. What's in front of the x squared? It's an 8. Hey, it's inconvenient that I underlined it for you. But does the process change? No. The process doesn't change at all. It's just adding 2 steps to it. Okay? It's going to add 2 steps. Because what happens when you have that first term that's not equal to 1, you have to change your mindset of how do you finish the problem. Well, in this case, what we do is we still multiply our tails. 8 times negative 5. We have negative 40. And I need to add together to get negative 6. So we still start the problem the exact same way. We go through our lists. 140, 220, 4 and 10, 8 and 5 and 8. Which combination gets you to the negative 6? 4 and 10. Which one of those has to be negative? 10. The 10. The 10 has to be negative because 10 is bigger than 4. Therefore, when you put them together to make it negative, it had to be the larger of the 2. So what we're doing here is I'm going to take this from being 3 pieces. I'm going to make it into 4 pieces. This is called a couple of different things. It's called either factor by grouping or split middle term. Obvious reasons it's called split middle term. What did I split the negative 6 into? Negative 10 plus 4. Because if I combined it, you're still going to get negative 6. Right? But by going through here, we're able to see which one of those creates that value. Now, when you get to an even set number of terms, x squared and x and a constant, what you do then is you're going to group those 2 independently of one another. Here's what I mean by that. And I know we did one like this yesterday, but it might have gone too fast. I throw parentheses around the first 2 terms, first 2 parts. 8x squared and a 10x. What do those guys have in common? What's their GCF? 2. X. X squared and x, they both share an x. So I can factor out a 2x. What's 8 divided by 2? X squared divided by x? X. Negative 10x divided by negative 2x? 5. Now, if you stop and think for a second, if you were to distribute that 2x back in, you'd get 8x squared minus 10x. You're undistributing. You're factoring out the 2x. You're taking the GCF. you do the same thing on the next part. 4x minus 5. What do they have in common? All they have in common is a 1. If they have nothing in common, they still have a 1 in common. So what was the sign in front here? There was a plus. So we just write down plus 1. And if I take a 1 out of anything, do I change it? No. Now is when you have to you have to double check your work. Are the two things that are in parentheses the same? Yeah. That's a good sign. That's a really, really, really good sign. Okay? That means you're on the right track. So if those two things are the same, what you want to do then is just write it down. And what's left over that's not in parentheses? 2x and a 1. 2x plus 1. And now you have your terms. Okay? I know that there are quicker ways to do that. I know that there are other ways of going about to get that. This method will always, always work. Okay? It takes a second longer than other ones, but it is a more straightforward, algorithmic, this step, this step, this step, than some of the other things. Yes, ma'am?
Do we only use, why do we only use one of the 4x minus 5?
Aren't these terms? What is 2 times quantity 4x minus 5 and 1 times quantity 4x minus 5 have in common? That's the GCF. And you're left with those two.
So you just get the GCF?
That thing in parentheses here,
Yeah.
that's automatically the GCF. What you're doing is you're technically finding the GCF twice. I just don't ever say that. It's a good question though. Okay. So now you have parts to equal 0. So you set them both equal to 0. If you set those both equal to 0 then, well, on the first one, what do you do first? Add the 5. Good. So I have 4x equals 5. And then what? Divide by 4. And I think yesterday you heard me say something when we had, I don't know, it was like 2x minus 7 or something. I said, oh, just add 7 divided by 2. That's where that was coming from. Okay? That's where that was coming from. You okay? All right. And then what do you do on the other one? Subtract 1, then what? Divide by 2. So you would subtract 1, and you divide it by 2. So your 2 zeros, in this case, would have been at 5/4 and negative 1/2. Now graphically, that one would have been awful to figure out. But that's why we learned about the algebra style of it, to get us to be able to still figure out what your answers are, what your zeros are, okay? Is fogginess being blown off a little? Hoping? If any section, this is the one that we do it a lot in. We do a ton of it. Excuse me. So here we have a 5x squared minus a 13x plus 6. What are your tails? 5 and 6. Yeah. So you multiply your tails together, and we're going to get 30. And they have to add together then to be negative 13. That should tell you something different. If two numbers multiply together that are positive, but yet they add together to equal negative, what do both those numbers have to be? Negative, good. They have to be negative. So now we just go through our lists of 30. Well, 1, 30, 2, 15, 3, 10, 5, and 6. Which of those combinations being both negative gives you 13? Negative 3, negative 10, right. I mean, 2 and 15 will get you there, but one has to be positive, one has to be negative, so it wouldn't technically work. So we know that it has to be negative 3 and negative 10. Okay? I do the exact same thing. When I set that up, I'm going to rewrite it as 5x squared minus 3x minus 15x, oops, sorry, not 15, excuse me, 10x, and then plus 6 is 0. And once again, what we've done is we've taken that negative 13 and we rewrote it as negative 3 and a negative 10. We knew it had to be those two values because we worked from the tails of the 5 and 6. Miss Chloe.
Can you go the other way?
What do you mean? Oh, put the negative 10 first?
Yeah.
Yeah, absolutely. Absolutely. You're going to get the same answer when you go through that. There's a reason why I did this one second, because notice both middle terms, they're both negative. And the one I did a second ago, I had a negative and a positive. When I have that, I always put the negative first. It's a little less cumbersome, because here, I'm going to have to do a trick on my second term. All right. So what she's asking us, because negative 3 and negative 10 still makes negative 13, negative 10 to negative 3 still makes negative 13. You can flip-flop them either way. What's wrong, Tope? You just had a quick look. I was making sure. Just making sure. Yeah, yeah. All right, group it. What do those guys have in common? 1 and what? X. Do I have to put the 1 down? No.
But you can't.
Now here's the trick that I want you guys to see about when your third piece is negative. You may or may not remember this from before. Usually what I do is this. I will do a plus minus and then make it negative inside the parentheses. The reason that I do that is because I want to think about, all right, knucklehead, I need to remember to factor out a negative. It's just there to remind myself, bozo, take the negative out. So no matter what, I have to bring out a negative, but what does a 10 and a 6 have in common? 2. Negative 10 divided by negative 2 is 5. So it's 5x. Positive 6 divided by negative 2 is negative 3. Are these two the same? Yeah. Now, Chloe, if you did it your way, you had your in parentheses was an x minus 2, wasn't it? It's just the opposite. These two are the same, so I write it down. What's left? X minus 2. Okay. So now you have two terms. Oops. You have two terms then that you can set equal to 0. One of which you would just have to add 3 and then what? Divide by 5. So one of them you're going to get add 3 divided by 5 and x would equal 3/5. And then on the other one you just have to add 2. And those are your two zeros. The zeros are created from terms. That's where all this comes back and forth to, okay? I know it sucks, but it's one of these things that doesn't go away. I just wanted to make sure we got this because there's a lot of it in here. I want to make sure you guys are all right, okay? Let me give you a handful for this evening, and then we'll go over all this stuff tomorrow, because I know that this will help those of you guys that are struggling a bit with the factoring portion of this. What's that? Not yet. You know what? You want to do this? Hey guys, if the book stuff didn't work for you and you can get a picture of it, grab the book and just take a picture of it. You want to just do that? I don't know why you did that. I'm going to try and figure that out. Your guess is as good as mine. So on this one, I just want to use the calendar. That's all I'm asking.
I just said it's 118.
On what's coming forward, do those, please. There's a mixture of factoring. There's a mixture of some of them are just solved for X. Is there spares? I'm sure you don't need like 17 of them.
Yeah, I have.
All right, we'll do those. We'll go through some of the extra factoring junk that shows up from time to time. I counted you guys. I can count 4. It's okay. All right. Do them on a 7-sheet paper so you have some space. We'll go from there. Okay? Did it help to put the brakes on with the factoring? I mean, honestly, this might be the last tough section that we have throughout the year. Well, there might be one more, but as far as, yeah, it's regular polygons. You're right. Regular polygons with 15 pages, there's a lot going on there. All right. Yeah. They're a little ahead of us. I think she's planning on doing projects. That's why she got ahead to have time for it.